All right, I put an announcement up this morning for homework. I haven't assigned it yet, but I gave you some things you can be working on right now. Let me pull that up. So under discussions, homework 1. I'm recommending that you go to the R cookbook and go ahead and start reading there. I gave you some specific sections in the book. This is a fair amount of reading. Depending on how much background you already have, you can probably go quickly through some of this. But have a look at our cookbook, these sections. This will help you with doing the homework that's coming up, which will be basic R, download a data set, make a few graphs. And then we had talked last time about getting background on basic statistics. And I think I mentioned another book on an announcement. But the textbook that you have for this class also has some basic stats stuff in the first 3 chapters. So check out the first 3 chapters of the regression book. What I was going to do today is go and start playing with data in R. This week, my goal really is to go over exploratory things that we do with data sets. I said last time that step 1 when you have a data set is to look at it, make pictures, compute summary statistics, that kind of thing. So I'm going to give you an introduction to R with a real data set and start introducing graphics and summary statistics that we can do to explore a data set. All right, so under course content, there's a data set called HERS data LDL. So right here, HERS data LDL.csv. So I'm going to save this to my hard drive. And then I'm going to go to the scripts folder here on eCampus and get an R file that goes with that CSV file. So here's HERS LDL.R. Okay, so now let's open up this R script. Any R script, any R file, I said last time, is just a text file. So if you double click it on your computer, your default text editor is going to open it up. And not every text editor is as handy for dealing with R code. On the Podium computers and Blocker, Windows machines, I use Notepad++ as the text editor. It's free software, you can download it online. On my Mac, I use what's called Text Wrangler, and there's nothing magic about that particular one, but I like it. It's free, you can download it online, and it has some bells and whistles that make it easier to write code. I'm going to open HERS LDL.R in the text editor. So remember, as you are learning how to use and write your own R programs, make files like this. Don't go to R when it's time to analyze a data set. Don't come over here and read the data inside R and then make a plot over here and then do a t-test over here. If you do your analysis that way, you've got all your results right there in front of you, but if you want to share them with me, it's harder. You would have to come and show me, watch what I do as I run all these commands. But if you put it all in a text file like this one, I can send you, I could send you the CSV file, and I could send you this text file, and you could completely reproduce whatever I did. That's handy whenever you have errors, you're working on your homework and you're stuck, you can't get the code to do what you want. If you wanted to email me or our TA to ask for help, it will save everybody a lot of time if you can send your script and say I'm having a problem at line 44, for example. All right. So here we are in R, and I want to read in, load some data. All of our data sets are CSV files in this class. There's multiple ways to read in data in R. Since we have CSV files, we can just use the function that's built for those called read.csv. So I want to read the data in. I copied this, and now I'm going to paste it over here, and it's going to complain. Actually, it won't complain. If I had not already set the working directory of R to be the place where this file is located, then if I said read the file named this, it would complain. It would give me an error saying I don't see that file. But since we have changed the working directory, remember on a Windows machine you can come to File, Change Dir, and on a Mac you can go to Miss, Change Dir. But you need to have R pointing in the right place if you want to read in a file. So let's read in this file. If you type, this is the kind of thing that you'll learn when you read the first parts of the R cookbook. But if you type ls, open close parentheses, it will tell you all the objects that you currently have defined. So having loaded a fresh version of R, nothing's in there yet, we read in one data set, and we took the result of the read.csv function and we assigned it to the object named DTA. There is now an object named DTA available to us in the R workspace. What is DTA? R has objects of different types or different classes. You could have a true-false object. It has to be either true or false, a Boolean object. You could have a binary object, has to be 0 or 1, or a collection of zeros and ones. You could have numerical, you could have character, you can have categorical. R calls categorical variables factors. I'll talk about that some soon. When you read in a data set from, say, a CSV file, by default what you get is a data frame. Check out data frames in the R cookbook. A data frame is basically R's representation of an Excel spreadsheet full of data. Individuals in the rows, variables in the columns. We can think of it like a fancy matrix. R also has object types called matrices. All a matrix is rows and columns full of stuff. But a matrix in R, all the elements in the rows and columns have to be of the same type or class. So you could have a matrix full of numbers, or a matrix full of characters, or a matrix full of Booleans, but you couldn't have a matrix with a column that's categorical, a column that's text, a column that's numeric, and so on. That's why a data frame that's R's default way of representing data, because often you will have data sets with a mixture of variable types. Let me open our data, and we can just take a peek at it here. HERS data LDL, open it in Excel. So here's our initial data set. It's a fairly big one. We have 2,763 people. There's 2,764 rows because the first row contains the column names. And so for each of these people, we have a variety of things. First column is going to be like a treatment group indicator. Did this person receive a placebo or hormone therapy in this case? We have age, numerical variable, race and ethnicity, categorical, 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 categorical. And we do have a fair amount of kind of interesting numerical variables like weight, body mass index, waist circumference, WHR. What is that? I'll have to look that up. Weight height ratio. Yep, it's a ratio. That's probably right. Glucose count, and then over at the right we have total cholesterol, LDLs, HDLs, triglycerides. Lots of interesting stuff. When we read this into R, we're going to get a data frame, and each column is going to be of, hopefully, the appropriate class. So it will recognize that, for example, that's a categorical variable, and this is a numerical variable. We have read the data in. We now have an object named DTA that contains a data frame with our data in it. Here are some other things we might initially do with our data. Let me come back to my script. First thing I would do when I read in a data set is ask about its dimensions. What's the size of the data set? When you ask for dimensions of an array object in R, it gives you two numbers. A two-dimensional array has rows and columns. So this data frame has 2,763 rows, 37 columns. Next thing I might do is take a peek at the first part of the data. So if you just typed data right now and enter, it's going to fill your whole screen. That's not very useful. If you want just a peek at the first part of it, you can say head of data. And that'll give you, turns out, the first 6 rows. So this is just a subset, a quick look at the top of the data. There's also a tail function that you can use to look at the end. I'd also run the summary function on the data set. What summary does is summarize each column, so each variable. The first column was treatment indicator. Did the patient get the hormone therapy or placebo? The second variable it recognized as numeric. So for numeric variables, it gives us numeric summaries. The median age, the mean age, the 25th percentile, called the first quartile, and the 75th percentile, as well as the minimum and the maximum. Categorical. So for a categorical variable, all it does is tabulate the number of times each of the different categories showed up. So we have smoking, we have drinking, yes or no. Something interesting about drinking is there's apparently 2 people who had an empty result for drink. 1,680 of them said no, 1,081 said yes, 2 of them, it's blank. So we're going to have to deal with that. If you tried to compute the average of a bunch of numbers and one of them's empty, R is going to need some advice on what you want to do. We have exercise, physical activity, GLOB rate. I'll look that up. Maybe that's like global health rating, self-assessed. Okay. All right, so we have lots of variables. We have at least one data cleaning issue, and that is these missing values for drink any. Looks like there's missing values for this variable as well, and this variable. We also have some NAs in the data, which is another way of saying missing data. The weight variable has 2 individuals for whom we have NA instead of a weight. And again, if you try to do arithmetic with a variable that has an NA in it, R is going to complain. So this is as you would expect in the real world. You have a big data set, lots of variables. Some of the variables may be more interesting than others. Some of them may be completely redundant with some of the others. And you're likely going to have some messiness, some practicalities of just dealing with real data where there's issues. All right. So this right here, what I'm doing here, okay. DTA is our spreadsheet brought into R. Now, if you want to access one of the variables in DTA, so the column names of DTA are those. Those are our variables. Suppose I wanted to look at age, like let's make a picture of age. There's multiple ways to do this. One way, if I want to just look at age is the second column, the second variable of the data object. So I could say, this is something you'll see when you read our cookbook stuff. And let me back up real quick and just make a toy example first. Let's say we have a little object called x, and it is the numbers 1, 4, and 10. So I'm concatenating, that's what the little c is. Just put together 3 numbers into a string of numbers, or a vector. Now if I say ls, there's data and x. And if I type x, I get back my vector. If you have a vector, or an array more generally, and you want to pick out a subset of it, like suppose I just want the third element of x, not the first or the second. The way we subset objects in R is with square brackets. So if I say x square bracket 3, that says give me the third element of x. If I say 2, it gives me the second element. If I said 1 and 3, it gives me those. If I said 2 colon 3, that means 2 and 3. If I said x minus 2, that says give me x except for the second element. So pull out the second element. Now suppose we have a two-dimensional array. Let me make a new x. I'm going to make it to be a matrix, and I'm going to generate some random data to fill in the matrix. So here's 12 randomly pulled out, normally distributed data. Let's put them into a matrix that's 4 rows by 3 columns. So X is an array now, 4 by 3. To R, it's a matrix, a numeric matrix. All right, so now suppose I want the second column. If I just want the second column, because this is a two-dimensional array, when you ask for the dimensions of this, it gives you 2 numbers because there's 2 dimensions. So if you want to use square brackets to subset this, you need to tell R about which rows you want and which columns you want. If I want the second, or let's start with, if I want the first row, second column. If I just want this number right here, then I can do X first row and then comma second column. A two-dimensional array, you can index pieces, you can subset pieces by doing which row or rows do you want, comma, which column or columns do you want. So there's first row, second column. Now suppose I want the whole second column. The way you can do that is to leave the first index blank. So I'm going to say blank, comma, 2. That just means give me all the rows, but only the second column. So these are the 4 numbers in the second column. All right, now let's go back to DTA. We have this as our data set, and I want to look at age. Let's make a picture of the age variable. There are a couple of ways you can do this. So one way is to pull out the column that corresponds to age. Age is the second column. So let's say we are going to investigate the age variable. We could do data second column. We could also do data name the column in parentheses. We could also do data $ column name. And we could do with data age. The last two, data $age, works for any data frame. If you have a data frame and the columns have names, you can always see the names of your columns with either call names or just names. Both of them will give you the names of the variables. So you could say data $, any of these names, and get that column. I'll use this some as well. If you have a data frame and you want to reference variables defined inside of it, to avoid having to do like data $ all the time, you could just say with this data set, comma, an expression. In this part of the function call, age, if I just typed age over here in R, it complains. It doesn't know what age is, even though there's a variable named age in data. The way that R works is such that it won't know the variable names in your data frame unless you do something to clarify. I could do that. I could do this. If I say with data, then I can just refer to the column names without any prefixes. So I could have like age minus LDL, divided by whatever, HDL or something. You'll get plenty of practice with loading in data sets as data frames and using the data, manipulating it. So let's make a picture of the age variable. Yes?
If you just do with data, can you call age at any time after that?
Yes.
As its own variable name?
You mean like after you have closed parentheses?
If you close just before data, or after data.
Yeah, anything in here, you can just name the columns.
Okay.
Once you've closed the parentheses, that's done. Okay, so age variable. When we did summary, we saw some basic information about age. The minimum was 44, the maximum was 79. The mean and the median were very close to each other, around 67. So that's helpful. That's summary. I would call those summary statistics. Like what's the average, what's the mean and median, minimum and maximum. We might also want to look at a measure of spread, like a variance or standard deviation. In addition to basic summary statistics, it's a good idea to make pictures. So let's make a couple of pictures of age. Let's make a histogram. So with data, make a histogram, HIST, of age. Looks like that. So you guys know what histograms are. They bin the values of a numerical variable and then just count how many times you saw values inside each of the bins. So there were, like 10 people who had ages between whatever that is, 44 and 46. Most of the people were over here where the bulk of the frequencies are. You would call this a left-skewed distribution in the sense that it looked like you grabbed the left tail and pulled it towards the left. It's kind of leaning towards the left. You call that left skew. If it was leaning towards the other way, you'd call it right skew. That's a histogram. Here's another picture that we'll use, box plot. Box plot is just a coarser view of the data. Histogram has more granularity to it, more detail to it. Box plot is all it is showing you where the median is. That's the dark line in the middle of the box. And here's the 25th percentile, the lower bound of the box. And here's the 75th percentile, upper bound of the box. And then the whiskers go out to, usually they go out to the minimum and the maximum. But whenever R deems a point as being too far away, a potential outlier, it gives it a dot instead, like this. So I think what R will do in terms of defining outliers, you guys have probably heard of outliers, and the idea of an outlier is a value that's substantially different from the bulk of the data. There's no formal definition for what makes an outlier, though. So ultimately, it's really a subjective assessment. There are rules of thumb that are used somewhat commonly for defining outliers. One of which is, so if this is the 75th percentile and that's the 25th percentile, then the difference between those is, or the interval between those is the interquartile interval. 75th percentile is called the third quartile, 25th percentile is called the first quartile, and their difference is called interquartile range. It's a measure of spread. The inner 50% live between those two numbers. So what R does when it's deciding whether to put a dot here or let the whisker go on down is it asks, are any points more than 1.5 times the interquartile range from one of the edges of the box? So interquartile range was this height right here. Here's the lower bound of the box. So if we went that height and another times half of it, these points are just beyond that, so they get little dots. That definition is not a big technical point for you as a data analyst. Just be aware that whatever software you use, it'll have some rule of thumb built in for highlighting points as potential outliers. Just because a point is highlighted as a potential outlier doesn't mean that it's an outlier necessarily. It certainly doesn't mean there's anything wrong with the points necessarily. But if you do have evidence of potential outliers, you want to at least look into it. Go look at the record where the data came from. If this is, look at the record the data came from. You're looking for, is there any reason to believe that there was an error in the way the data was recorded? Should it have been 20, but it was put in as 200 accidentally or something? Or any other unusual feature of that individual. If it's an outlier, what that would mean to you is that really it doesn't represent the population you're interested in. For example, suppose we wanted to talk about the average or typical income of people who live in Seattle, Washington. If you went out and got all the people, suppose there's 200,000 people living in Seattle proper. If you went and got all of them but one, let's say we keep Bill Gates out of it for a moment, but we get 199,999 people and we get their incomes, annual incomes, we average them up. If we brought in Bill Gates to that calculation, what's going to happen to the average? It's going to go up substantially because outliers affect means. An average is just add everything up and then divide by the number of things. So if you end up adding a really big value or a really big small value, it'll affect things. So if your interest is in what's a typical person make in Seattle, you could consider, is Bill Gates an outlier? He's an outlier if you don't really have him in mind. He's not typical. I'm thinking about the average person, the typical person who didn't found Microsoft. So the question of what to do with outliers has to do with, does this person belong in here or not? Or individual, whatever it is, an animal or a plant or whatever you're studying. Is it representative or not? And if it is, if you are talking about the whole population of Seattle and we're allowing for some really smart tech people to have been there, then he belongs in. There's no reason for us to assume or require that our data look real pretty and nice. Often in the real world, data's messy, which includes outliers. And so let me just caution you to be careful with what you do with outliers. They're often there, and you definitely don't want to, as a blanket strategy, throw them away or replace them with another number that you think is better. You really want to think about, is there anything wrong with the observation? If not, is this person really representative of the population of interest? If not, then by all means get rid of it. And if it's an error, by all means fix it. But if you can't find any real reason to say it doesn't belong there, you really have no business getting rid of it. All right. So what I want to show, where I want to go next, is we've seen how to compute really basic summaries and how to make really basic pictures. What we haven't seen yet is how to relate multiple variables, variables to each other. We're just looking at one variable at a time so far. So let me introduce one more picture. And then where I want to go after that is let's talk about a couple of a little more sophisticated analysis or exploratory techniques. So we will talk about cluster analysis, and we will talk about principal component analysis. And we will talk about what's called correspondence analysis. So let me just say something big picture about each of these. Cluster analysis, what we're going to do is come back here to our data and gather up all the numerical variables. So there's some techniques for summarizing and visualizing that are specific to numerical variables. Then there's some techniques that are specific to categorical variables. Let's start with numerical. If we were to grab all the numerical variables like age and not that one, weight, BMI, and all these different ones over here, what cluster analysis would do is group the individuals, group the people together in terms of similarities among their numerical variables. So imagine you take a person, let's pull out the numerical variables real quick. Names, data. So we have age, pull out numerical variables. The numerical variables are, I'm going to write down their names. Age is one of them. What else? Height, or weight is the next one, I think. Weight, BMI, waist. I guess we'll do weight-height ratio. Glucose. I don't know what these with the ones after them are, so I'm going to ignore those for now. Total cholesterol. LDL. HDL TG and systolic and diastolic blood pressures. So SBP and DBP. All this is, I'll post this script, the revised version of this script to eCampus after class. But all this did so far is create a vector with all the variable names that are numerical. And I can now do this. So data, let's create a new data object called data underscore num for numerical. And it is going to be the original data, and I think I can just say num vars. Those are all the columns I want to pull out. So let's see what happens when we do this. Undefined columns. So I may need to do, it is case sensitive, but I think I got the, BMI caps. Thanks. Let's see if that did it. Okay, thanks. Now we have a new data frame. Same number of rows, but now I only have 12 columns because it's just the numerical variables. All right. So let me show you what cluster analysis looks like. I'm going to ask you to do cluster analysis on your homework, and principal components and correspondence analysis. These are methods that we're not going to go into depth with the mathematical detail. If you're interested, you might take 636 with me sometime, multivariate statistics. So I'm going to focus on showing you how to use it and how to interpret it. Okay. You can learn how to use and interpret cluster and PCA pretty easily, I think, without having to know about the matrix and linear algebra that underlies it. To do clustering, there is a function called hclust. So hclust is a function we're about to use, okay? If you want to know how to use a function in R, like what are the argument names and what do they mean and what's it going to give me back, do question mark function name. Pulls up documentation like this, and all the documentation files in R have a similar structure. They have basic usage, which lists all the arguments of the function, and then there's an argument section that tells you details about each of the arguments. Do they have a default value? What are the possible values? Stuff like that. Details section tells you what the function does, like what algorithm is being used, what's the methodology that's being used, and value section that tells you what you get back. So when we call hclust to do this thing called clustering, we're going to get back an object, and that object is going to have pieces to it, or items to it. I can take the object that comes back and pull out an element called merge, pull out an element called height, and so on. At the bottom of every help file, there's a See Also section, which provides links to functions that are relevant to what you're looking at currently. They might be other functions that do the same thing, or they might be functions that you call after using the one you're reading about. And then it ends with examples. So example code that shows you how to use the actual function. Just a warning, the examples in the help files are often, I think, unnecessarily dense. It's like people want to show off how good a code they can write, how clever it can be. You're going to have a better experience, I think, looking at the R cookbook for basic examples. And the R cookbook does have a section, I gave you the section in the discussion board, for cluster analysis and for principal components. And if you want more documentation on those methods, let me know. I can get some. Okay, we've got just a few minutes, so let me go ahead and do a clustering. What we do when we do clustering, we have 12 variables. 12 variables. 2,700 people, each of which we have 12 variables. Cluster analysis, we're going to take the 12 numbers. Think of that just as a vector for each of the individuals. So we have 2,763 vectors of length 12. They're all numeric numbers. So we could take two 12 vectors and compute a distance between them. How close is this individual to that individual in terms of their 12 variables? You could compute, say, Euclidean distance. Square difference, component by component, add them up, take the square root. With 2,700 people, we could compute all pairwise distances. So we could compute a 2,763 by 2,763 distance matrix, a matrix of distances. The first row, fourth column would be the Euclidean distance between person 1 and person 4, and so on. So imagine this matrix full of distances. What clustering is going to do is look among all of those distances and find the smallest one. Who's closest? Out of all the pairs, which two are closest to each other? Those two, in step 1 of the algorithm, get put together. So instead of 2,763 individuals, now we have 2,762 individuals, or 2,761 individuals, and a cluster containing 2. We currently have 2 people put together. Then what you can do is recompute the distances and repeat. Now that we've joined those 2, we have all these individuals and a, quote, cluster of 2. Now do distances again and join who's closest now. It could be 2 individuals that you join again, or it could be that one of the individuals needs to be joined with the cluster of 2. So let me show you a picture that highlights or explains this, I think, pretty well. To do hclust, I'm going to say hc is hclust. You can name any object whatever you want. I named this one hc just because the function starts with the letters hc. I do recommend that you be careful about what you name things. Try to be intuitive as possible, so when you go back and read your code later or you share it with somebody, you don't have like variable 1 through variable 100, because that's hard. I have no idea what the meaning behind those are. HC, hclust, and I think what we need to do is call the distance function data num. Okay. So in order to do hierarchical clustering, which is what we're doing, there's different types of clustering algorithms. The one that I was describing, compare all the individuals in terms of their vectors and put people together who are closest to each other, it's a hierarchical algorithm. And it needs distances. That's what it works off of. Clustering is all about distances because it's trying to group people in terms of smallest distances among them. So to call hclust, we give it a distance matrix. And you can create this distance matrix. By default, these will be Euclidean distances, but there are different choices of definition of distance. Give it a 2600 by 2600 distance matrix, and then it gave us back the results. Remember when we looked at the help file, there was the section that said value. Value is what comes back to us. What's the class of HC? It's an object of class hclust. So it's a specialized object that has elements and structure specific to an hclust call. What is inside? There are elements to HC. There's something called merge. There's something called height. I'll show you what those mean probably next time, but let me just show you a picture for now, and we'll quit with this. So HC is the result of doing hierarchical clustering. let's print a plot HC. Plot is a generic function in R. It will do different things depending on the type of the object you put into it. So there is a plot method specific to hclust. It knows what to do with an hclust object. And this is what it looks like. Kind of messy. It's a tree-like structure. Tree-like structure. There are 2,700 and something little nodes way down at the bottom in the grass. Can't really see it because there's too many things on the plot. And if you went to the very bottom, I'll show you a toy example next time that makes it easier to see. If you go down to the bottom, you'll see there's at the lowest point down, two individuals got joined together. The height at which the joint happened is equal to the distance between those two individuals. Then distances are recomputed, and we look for the smallest distance again and join. Recompute distances, look for smallest, join. So all these little merge points are basically like nearest neighbor clusters being joined together. And we're going to learn how to look at this picture and decide, are there clusters? Because there's no guarantee that there are clusters in a data set. Clustering refers to like structure. There's something systematic about individuals that move together, have similar characteristics. Suppose you just generated randomly distributed data, everybody's independent of each other, there's no relationships. You could still do clustering, but there's no clusters. So we want to know how to interpret a picture like this. Is there clustering? If so, how many clusters are there? And what can you tell me about what makes each of the clusters distinct? So we'll talk about that next time. For now, go ahead and start reading our cookbook and the textbook. We'll keep going on Friday, okay? Thanks.